Good evening, sir.
Just give me the privilege to share my slides, ma'am.
Yes, sir. I have made you the co-host, so you can share your screen. Can you check, sir? Are you able to share the screen?
Yes, ma'am. It's working, not issue.
Yes, sir. So the participants, we can move on to our next session, and that is our final session of this FDP. It's on futuristic paradigms in quantum computing. It is my privilege to honor and invite Dr. B. Balamurugan sir to deliver this session. Dr. B. Balamurugan is a distinguished academician and researcher who currently serves as the Associate Dean of Academics at Shiva Nadar Institute of Eminence, Delhi NCR. He is widely recognized as one of the top 2% of scientists worldwide by Stanford University for his impactful contributions in the field of data science, artificial intelligence, and machine learning. Dr. Balamurugan is also an adjunct professor in the Department of Computer Science and Information Engineering at Taylor University, Malaysia. Before his current role, he served as a professor and director of international relations at Golgotha's University, Greater Noida. His academic journey includes 15 years of experience at Witt University, Vellore, where he held the position of associate professor and contributed extensively to the fields of engineering education, blockchain, and data sciences. With over 200 high-impact journal publications in Springer, elsewhere, and IEEE, more than 200 authored and edited books, Dr. Balamurugan has established himself as a prolific contributor to academia and research. He has collaborated with eminent professors from top QS-ranked universities worldwide, further solidifying his global presence in the academic community. Dr. Balamurugan's dedication to innovation and academic excellence is evident in his contributions to curriculum design, accreditation processes, and his involvement in consultancy projects. He is a sought-after speaker, having delivered over 300 talks at prestigious events, and has been instrumental in organizing more than 10 IEEE and ACM international conferences. His passion for teaching, combined with his expertise in quantum computing, design thinking, and emerging technologies, promises to make this highly engaging and insightful session. Thank you so much, sir, for accepting our invitation. We welcome you to the session. Sir, your voice is not audible, sir. You can unmute yourself. Yes, sir.
Thank you. And you can see me also. You can see me as well as the PPT is ready. Am I
Yes, sir.
right? Okay.
Yes.
Anyways, thank you participants for being here, and thank you Professor Shilpa Reddy for inviting me for this wonderful topic FDP. And especially nowadays, the last few years is seeing a lot of quantum related topics coming in. So since I'm placed in Delhi, I will first start with why we have to learn quantum. Like every country, like or fighting with each other of who will become the quantum superpower. So whenever a new technology comes, imagine a technology like blockchain came before 2 years. So a lot of countries started doing a lot of upgradation in terms of research, academic, and in IT. So all this were happening. Now what is happening is new technology has come. Imagine artificial intelligence. A lot of countries again did a lot of innovation in artificial intelligence. So those country who are part of this artificial intelligence movements are considered to be the top countries in the world. So, for example, if you take India, like how we have Buffalo in United States, we have Bangalore in India, where a lot of innovations in artificial intelligence has happened. So, how to measure it is how many number of startups have come in artificial intelligence, how many of common people have started using artificial intelligence. So, by which we can quantify and update things. So same like that. Now the quantum movement has got. So what is the purpose of this quantum movement is like educate people. They should also know a little bit about quantum and they have to work something related to quantum and they have to also do some application related to quantum. So we have previous lectures and other lectures talking about it. So my lecture will be like more based on how you can integrate high performance computing and quantum in order to give a edge over the previously available like computing available. And I will also be specifically emphasizing on like the industrial digital twin that is available. So if you take industrial digital twin, that's a way of doing simulation. So that's a kind of way by which you can do simulation. So we will be talking about that too. Like if you take quantum computing, like it is a kind of expensive tool for doing it. Okay, so then you can ask me like why we have to learn a quantum computing. But us being a professors and being postgraduates and someone who is doing research, there are still a lot of opportunity that can be done on quantum computing. There are a lot of free tools, there are a lot of free programming language that are available, or there is also possibility of using the existing programming languages in order to do the quantum computing. So I will be talking about little projects that can also be started by individual so that you will be part of the quantum movement. And in terms of faculties, they are very keen in publishing contents. So for example, take it to book chapter, it can be a book, it can be in a journal paper, it can be a scopus paper, or it can be a conference paper. So what all these venues look for is novelty. They'll be always looking for something like what novel he has done. So whether he has done something new. So whenever you are working on different areas, what will happen is the novelty will be less. It means like already much of things would have already happened. So it's very hard for you to communicate some novelty. But if you take quantum, the good thing about the quantum computing is there are not many papers out there. Means recently they have added a lot of papers and content, knowledge content out there. But slowly what will happen is you will be able to do something more on quantum computing when you are doing on academics. Even I will also show some of the publications which we have done in top journals, Q1 journals like IEEE Access and scientific reports. I will show you that. Okay, so basically, like why quantum computing has come. So always the solution comes or a new area comes for a reason. That uh, like we need to. It comes for a reason that we need to like do something new. So what is the purpose of doing this? Okay, so like if you take blockchain, why it came is because it has to come out with a new novel uh, technology by which we will be able to like secure items or secure attributes or secure databases without any middle part. Okay, so that is the purpose of blockchain that has come, and blockchain has been implemented and people are using it. There are many of the government services what we are using, even our Aadhaar card, all the transactions related to Aadhaar card to and fro are being like customized and being taken care by means of blockchain technology. If you take quantum computing, they have certain thing related to quantum computing. Okay, so we divide everything into something called quantum information science. Okay, so already in our classical computing all this exists, like quantum networking means we have normal network computer networking there, and quantum computing is that we have normal computing, and we also do simulation using our binary computing, we also do cryptography, we also do sensing. So what is the difference between quantum and this? Okay, imagine like uh, if a traditional classical computing is like traveling inside a city in a car, quantum computing science is not traveling in a fast car, but it is traveling in a cruise around the city. So it is completely different, and it's not competitors for any of the things. Nobody can say that once quantum computing comes, the classical computer will be out. No, it's not the case. So these both are entire different paradigms, and it lies both in a parallel track. So both of this will hand in glove each other to solve unsolved problems in computer science. Plus this both will work separately in order to deviate and come out with certain solutions for every problems that are available. If you take computer science, like we will be dividing all the problems into different types. For example, we call certain problems as NP hard, like, and certain problems are solvable. The hardest of the problems are solved as NP hard problems. It means that it is not going to take a definite time to solve the problem. It means like we find out the complexity of solving a problem in terms of order of n. It can be order of n squared, or order of 0 or whatever it is. Okay, it's according to the amount of time in terms of computing time it takes. So it is called as computing complexity, and it can also be distinguished between time complexity and space complexity. And there are a lot of problems. For example, if you take computer science problem, especially that what we do with computer science is mostly are categorized into certain types. Like you take, there are classification. It can be computed. Okay, I can classify things. If you're giving an apple, and it has to classify as apple. If you're giving orange, it has to classify as orange. That's it. Okay. On the other hand, what will happen if you want to sort certain things? There are certain numbers, certain names, or certain attributes. You have to arrange it, sort it. Then it can be done by means of classical computing. You want to associate two things. You want to check whether this and this are equal or not equal, or how equal it is, how much percentage of this is inclined with this. So then you can do for it. So similarly, if you go for classification, clustering, association, sorting, searching, this kind of operation, or multiplying something, which is part of basic operations, or exponential of something, when you want to do in a higher level, or you want to quantify something, qualify something, all this can be done by classical computer. So how the classical computer works is by means of binary, zeros and ones. And like for classical computing, we use certain thing like silicon we use, where it stores the value of zeros and ones as a signals inside the chip. Which why we have chosen silicon is it can hold the charges for certain amount of time, which is necessary for doing this computing. So the problem is sorted. Now, like when you go for quantum computing, so when people felt this 2 bits, zeros and one are not enough, they went for something called quantum computing. So what do you mean by quantum computing? Like it will not only have 2 bits, but it will be having qubits, which can be more than two. It can be of any numbers you can have it. So it can be 3 qubits, 4 qubits, whatever you like. So all this can be taken into account for computation. For imagine when you are doing probability statistics, stochastic model, and all that using classical computing. In probability, the total probability is 1, the minimum probability is 0, and any probability that anything happens will be between 0 and 1. So that's all. It can be, if it is 50-50 probability of a coin being tossed on here, it is 0.5 for head, 0.5 for tail. But in case of quantum computing, it will give different values. For example, when you're tossing the coin on the air, what it will be doing right from the beginning of tossing of coin, since it takes 1 or 2 steps up in the air, it will find out how many number of heads were there, how many number of tails were there, and it will be doing computing and math. Then it gives which, whether head is more or tail is more. It depends upon multiple attributes by which the coin has been spinned. Okay, so but in a classical computing, we will not be able to record all the different faces of the coin. So that's the difference between that. Okay, now let us come to something called quantum information science. So take an example of quantum sensing. So what is quantum sensing? Even in classical computer, we have something called sensors. So what is a sensor? Like which are used for measuring something, for identifying something, quantifying something. It can be a pressure, it can be a weight, it can be a smell, or it can be understanding a chemical, whatever it is. So that's what is the purpose of sensors. On the other hand, quantum sensors are also sensors, but it will be more accurate than what we call as classical sensor. It will be very accurate. So accurate in the sense what? Okay, so like for example, if the normal sensor takes 5 seconds to find out whether there is smoke emitted, the quantum sensor can find it even in a better. And one more thing, if there is a smoke sensor in a classical computer and it needs this amount of smoke to be there in order to identify that, but on the other hand, like a normal quantum sensor will need even a small amount volume of smoke is enough to trigger the quantum sensors. Okay, like like sensor technology has been developed very rapidly. So we have n number of sensors already available. You can see like uh, we have like sensor everywhere. For example, sensors are available as a strip. So when you go for the blood strip sensor and do your blood test, at a second they will say whether you have sugar or any other disease or whatever can be found out from blood components. They will say immediately, because that's a powerful sensor available. Even sensors are used as part of all the electronics we use. It can be a mobile phone, it can be a laptop, or it can be your car. Okay, so the lot of development is have been happening. Okay, so especially in automobiles and electrical vehicles and all, the amount of quantum based technology they are going to use in further days will be more, because the decisions that are in critical systems like automobile has to be taken very fastly. So this quantum is going to help. But the what is the challenge is here? So the quantum computing, like classical computing, cannot be worked or put to work in a normal room temperature. So you can see that even classical computer in the beginning days used to be huge. It used to be as big as this room or a bigger space it needs. Now we have everything inside a small palm laptop, or in a small palm mobile phone. Okay, so but slowly they did a lot of advancement. They made all the parts of computer like very smaller, and they are using it. So that's so the same thing will happen also with quantum computing. So now a lot of research are going to be happening, and it's been happening on material science. So what is material science? Because as I told, classical computer use silicon for storing the signals in order to use it. On the other hand, quantum computing also needs certain kind of material which will have certain proton, electron, or positron movement inside it. It's atomic level movement inside it, which has to be measured. So that's what it is being done. So a lot of research is also happening in material science, because like other than the periodic table, there are millions of materials that are available in the earth in terms of alloys. So they are doing a lot of research which material can store signals, and so that I can use that in a normal room temperature. If not in room temperature, at least certain degrees of temperature it can be used. Now, if you take quantum computing, it is going to be very hard for you, as you can use quantum computing only in a minus 40 or 50 degree, and you have to getting that degree inside a normal working environment will not be possible at all. So that commercialization of any of this quantum technology is going to take time. So when the any of this kind of enhancements or advancement will become popular is when, like, if you feel like this can be given for a common man. Unless this can't go for a common man, none of the technology that has been invented will get into like popularity. So it has to go to the last retail, then only it is going to happen. So if you take quantum sensing, like it is growing like anything. People are doing a lot of research on that, and you can also see that like lot of application has started to come. So like what we are going to do by means of quantum sensing is, we are going to come out with some kind of advanced sensor technologies, by which a lot of advancement in terms of materials will happen, and also by which like the decisions are there, it also is going to happen. So if you see, like there are a lot of companies which are working on it. So like if you take, like there are companies like Qualcomm, IBM, like even Meta, and like you can always Apple. These people are working on quantum sensors. They are coming up with a lot of new sensors. If you go and type in Google what are the types of sensors that are there in terms of quantum, there are a lot of sensors available. So as a student or PG student, what you can do is you can start uh, already working on this kind of sensors that are available. Okay, so as I already told, normal sensors will have certain physical constraint, and this quantum sensing is going to make it into a much better way. Can you see my slide? Is there any?
Yes, sir. Till now it is visible. Yeah,
Okay.
yeah. Now also. Yeah.
Okay, so this is about quantum sensors. Okay, got it. So like as I already told, when you talk about quantum sensors, it will be faster, more accurate, more reliable. And imagine the geolocation accuracy we have in terms of the classical sensors. Okay, so it is to a point only. For example, if you take GPS devices, has also a lot of far fewer limitations. For example, it is dependent upon satellite, but when this quantum sensing is going to be like uh, taking care of this uh, geolocation, then it will be more accurate. Imagine, like, within the room you can travel, and it can find out each of the each of the distance in terms of millimeter or centimeter. It's going to be very nice. Now, if you take Google Maps, we have a lot of limitations. It works at a time, but it doesn't work for very short distance. Imagine you want to go from one room to another room or one hall to another hall. You really can't use Google Maps, but the possibility is going to come. And imagine, like, when you are using quantum sensors, the amount of diagnostic images that we have got from medical equipment will be more accurate, and it will be also be having few side effects. Imagine, you take up patients, if they are having more accurate images, I can easily like find out what kind of cure they need. Okay, so when you talk about sensor, don't think only about sensors related to IoT. Even a camera is a sensor. Do not forget, I'm repeating again. Even a camera is a sensor. Okay, got it. So a sensor has anything that does with identifying or measuring something. Okay, got it. So when you want to go for autonomous navigation, imagine we have EV coming up, we have autonomous vehicle coming up, we have self-driving cars coming up. All these are separate technology. So at that time we need this kind of quantum sensors, which will be like helping us to navigate like all these vehicles. And like we are coming out with vehicles like car or automobile that can go above in the air. Okay, so maybe in 5 years, 5 to 20 years, we can see a lot of traffic on the road. So people will start using cars that can fly a little high, maybe some 20 feet or 30 feet above the ground, and we can see vehicles going on. So now also it is possible, but it is kind of expensive. So people are restricting to get that into market. So and the vulnerability, like what we have by means of radio frequency signal, or in space or underground or any of the zone, is going to get less. Okay, so I can say it will we can go easily for a reliable detection of something by means of quantum sensor imaging, or we can go for any kind of imagine, like when classical sensors or anything, it can't used can be used in tunnels. When you go in the tunnel, imagine, do you get signal? No, not at all. But when you go for quantum networking, that possibility is there. Okay, so even you can use it in tunnels, you can use inside water pipe, mines, and subterranean habits. Now, because now we are using satellite phones for all this, but like um, now, since we will be going for quantum, which will be using atomic level extracting data, it will be easier. Okay, so you somebody would have told you about the factors that are in quantum. Like we have something called superposition, and like what is superposition? At a time, an atom can take two positions, and both the positions are interconnected, and one change in value of one position is going to alter the value of other. Okay, so this is called as superposition. I don't want to repeat it again, because I think for the whole lecture many would have told the same thing. Okay, so this is about quantum sensor and quantum sensing. We can talk about quantum sensor alone for 1 hour. That big a topic is, and students, PG scholars, and faculty can start doing it, because the government of India has implemented the Quantum India movement, and they have invested somewhere around 8,000 crores. So it means, why they have invested 8,000 crores means, like they'll be using it to fund faculties for doing funded projects, and they'll be using it to fund faculties for conducting FTPs and all other STTPs and any kind of development programs which involves these practices. So similarly, if you are working in quantum computing, your value also will be very good. It will be raised. So that's why you have to always work on latest technology. So if you take quantum cryptography, that's a very good topic to talk about. So now you have all the algorithms that are there as a quantum cryptography. So for example, you take like we have cryptography as fundamental for a lot of encryption and decryption. So if you take security, we can divide it into encryption, decryption. We can divide it into access control, we can divide it into digital signature. These are the three parts of uh, like uh, security in computer security. So what do you mean by access control? Who has to access what file can be defined. We have to create a profile for each and every individual, and they will be accessed. What do you mean encryption, decryption? When a data has been sent over any of the private channels. So imagine Airtel is giving, other companies are giving. So we can't believe any third party who is a transfer like a person for any of the data that has been sent through our mobile. So the mobile can be your choice, you can get, but the transmission has to be like somebody else's choice. You can choose out of anyone who are the nice transmitter. There are a lot of private players who are available who will give you free service, paid service for 5G, 6G, or whatever it is. So you have to choose. One of you can choose one company, another can choose another. So, but how people will choose that company is by means of understanding the security measures they take for that kind of transmission. So when you go for quantum cryptography, it is the highest level of security. So what will happen is like in the further slides, I have explained that also. You have to just wait for it. So in a classical computer, in order to break any algorithm, take an RSA algorithm, blowfish algorithm, or DSA, or any of the algorithm that you are using, or any of algorithm that are used like end-to-end encryption, decryption, they all can be broken by classical computer by so many of leaf years. It means it's going to take infinite number of years for you to break it. But on the other hand, if you have a quantum computer in your hand, the amount of time it is going to take to break the algorithm maybe in months, years, or days. So all the companies which all have a good cryptographic algorithm are now understanding whether the algorithm is quantum verified or not. I'm repeating again. Any algorithm you are having or you are making or you are creating or you are designing should be quantum verifiable. Okay, so that on the other day I went to a forum where Qualcomm was discussing about quantum computing. You know, they are completely integrating quantum into chip. They are talking about because India is going to become a place where ICs are being made. So they are investing heavily on VLSI, and a lot of companies are coming up and setting up industries in Noida, Greater Noida, and Delhi NCR region. Also in several other places south of India also. So like what they are going to do is they are going to do semiconductors. They are going to create semiconductors for many of the things, like it can be uh, a laptop, it can be for a mobile, and now they are integrating all the semiconductors uh, based upon quantum and AI. Imagine, so it will be very powerful for us to use it. Okay, so if you take what is the purpose of this, imagine aircraft manufacturers like they do certain equipments by which the devices can talk to the ground station. So when they are using any kind of decryption encryption, somebody can break it, they can misalign the traffic signals of an aircraft and they can deviate to some other place. So this quantum cryptography is of very good use, like, and many people have started using this. And one more thing I want to add here is like quantum cryptography, like like any other thing, can be done by a lot of people like us. So we need not to uh, have real quantum computing technology inside it. There are a lot of algorithms which can be theoretically written. Okay, so like how we are going to transmit the data securely is the fact that we will be studying in quantum cryptography. So if you take normal cryptography, what will be there? There will be key distribution. There will be like key exchange. There will be encryption. There will be like decryption. All that. And what are the applications we have? Each and every application what we use is secured. Okay, even if you use a like UPI portal for paying amount, it is imagine if there are no not a kind of security that is available, the hackers will be let free and it is going to be poisoning the entire system. So today morning also I went for a meeting like where people for a high level uh, kind of conference where people were talking about how many of times hackers are very vulnerable, they are creating in all the main systems of each of the governments, and how people are working hard in order to find out the better way of securing our data. Imagine, take a bank, all the money is in numbers, so it's going to be very hard tackling it. Imagine the people who are working behind all this. Okay, so in order to make this reality, a kind of cryptography is there, which is called as quantum cryptography. So this future will be like understanding the security, and it will be more better. Means nowadays you are using mobile, lot of devices. Every devices Even a water bottle will store money inside it. They are going to make that way. All the devices, your specs, your laptop, your glove, will have money inside it. So wherever you touch it, the amount will be just transferred. So you need not to have this kind of security like what we have now in order to do that. So once quantum computing based cryptography comes, and it can be easily implemented, then it is going to naturally solve all the disasters we are having. Okay, got it. So it will provide us flexibility. So imagine like a lot of applications can be made as a portal. Like imagine like you have a small cut in your finger, and you are just like putting inside a small chip. And imagine if this chip is having a power of quantum cryptography, like the chip can be connected to your bank account. So wherever you go, you need not take even a mobile phone. You can just touch the chip, and you can talk as a phone to anybody else, keeping near your ears or in loudspeaker, or you can use that your small finger in order to talk to somebody or transfer money. So that's what they are leading. Okay, so all the hardware selection or protocol choice or distance consideration in quantum cryptography can be decided, and all these are what I'm speaking are not imaginary, but a feasible imagination which top scientists in top companies are doing, and they are on the way to make it a reality. Okay, got it. So then what we are going to talk about is quantum networking. So okay, so what network we are using, like traditional network. So what are the things that are happening? Like we are transferring data, and what is the development that are happening? Like yeah, a lot of development is happening. For example, if you see like normal networking, we can send like how it started. It started with an standalone system, and after that, what happened is a lot of systems came. So like we made sure like uh, this kind of network is needed for transmitting data. Then it's not only about data, then we started transmitting images. Okay, it also helped us. Then after that we started transmitting videos. Then we are starting to transmit every details, like frame by frame, high quality videos. Now we are doing any kind of transmission, even encryption, decryption, money, everything. Imagine like, so what kind of network we have got is kindly like very challenging, but it also has certain vulnerabilities. People are not confident about sharing certain things over internet. So when quantum networking combines with quantum cryptography, it's going to do a lot of changes. Okay, it's going to give a lot of changes. Okay, so what are the basics of quantum networking? If you take like it is again distributed, but it is going to link multiple quantum computing processors that are available, and it is going to send qubits among them. Okay, so like now what we are having, we are combining multiple classical computers, and we are distributing normal bits, but this is going to transfer qubits among them. Okay, got it. So like this kind of quantum communication is going to help us. And the main challenge of this kind of quantum computer is this: the length, the distance. Okay, so when you are using classical computer, we still use something called tap. We use completely called like what amplifier, where the whenever after a particular distance, there is something called time to live, TTL. There is a perfect time to live for each of the data when it is going through a long distance. So after that, we will boost the signals, and then it can again move to lot of distances. Got it? That's what is being happening. So in quantum, there is a challenge over there. What is the challenge there is, like it can't travel for longer kilometers. Okay, so because the signal weakens, and since it is a quantum entangled qubits, will not be able to broadcast. So this kind of challenges is there. So while you are reading quantum computing, please make sure you understand the quantum concept, which is a theoretical concept. So I will explain it when the next slide comes. Okay, so uh, we don't have much of advancement in something called quantum repeater, which will be transporting qubits over long distance. That's what I'm trying to say. Okay, then we have something called quantum simulation. So what is a normal simulation is about? So when we want to do something, like what we'll do first, when we want to build something big, we will first initially build something on a small scale, which has to be replicated in large scale. So that kind of simulation or modeling is called as quantum simulation. So that quantum simulation is something that has been not in imaginary but in a fusible condition. Okay, so what it means is like we call it something called digital twin. Okay, so what is a digital twin? Like when we want to do something on a satellite which has been kept in moon, we will do something here which will be giving a reflex directly on the satellite that is kept on the moon. Okay, got it. So this is something called quantum simulators. Like you can see, like uh, simulators have also got an exposure. It has been growing over the years. Like before we had simulation in terms of modeling, we even, many of you would have used MATLAB and Simulink, and we would have simulated multiple transmission system, telecommunication system, or automobile system, or normal control system. Similarly, like there are a lot of problems where this kind of quantum simulation is need to be used. Oh, good. So if you would have studied theory of computing and you would have studied about Turing machine itself is a simulation of how a computer works. Okay, anything in this world can be represented as a Turing machine. Okay, there are a lot of problems that can be solved by means of simulations. So we'll be seeing to that. Okay, so now I think you would have come across all this uh, five things that are needed for quantum computing. Okay, so whenever somebody is speaking about quantum computing, like please do not think like it has been just invented. No, none of the technology can be invented within a day or within a year. It slowly progress, but as and when the need of that solution is needed, then people will start embracing it. Okay, so like they will start getting it into their academy or industry. So usually academia used to get new concepts done, but industry will catch with it and they will make commercialize of that, and they will go so faster than academics. That's what always happens. So if you see the early ideas of quantum computing, it has been started somewhere in 1979, where the word quantum is being used. Okay, got it. So like you should also be knowing that the quantum uh, computer idea is already there. We call it as quantum physics, where it defines about the quantum level of behavior of materials and how because of that the whole world changes. Okay, so that's all written in quantum physics. Then after that, from quantum physics you should be knowing about something called quantum uh, mechanics. Okay, so implementation of quantum physics from theory into certain uh, like level is called as quantum mechanics. And after that, quantum computing, automation of certain things in quantum mechanics will be done by quantum computer. So you can see the early ideas, which are some newspaper clips. So you can see people have started understanding about quantum, because people always say like the whole world is working in a quantum manner, not a classical manner. So certain things has to be simulated in a quantum computer based way. Then only it is possible for us to find a solution for it. Can any one of you say what are the problems that are there in the world that can't be solved? There are multiple problems. If you go to Wikipedia or if you go to any other Google and type, what are the unsolved problems in the world? Immediately you'll get a lot of problems. So a lot of people are already parallelly working for it. Many of the Nobel laureates work on open problems. So what do you mean by open problems? The problems that are not being solved by anyone for multiple years. Okay, or the problems for which the solution is given in a much better way. So that is called as yeah, like greatest achievement. Okay, so I think so far so clear. People are understanding. Can I get a yes or no?
Yes, sir.
Okay, ma'am. My
Actually,
order.
participants are muted in order to,
No problem. No problem, ma'am.
yeah, in chat box
Finally,
there are typings.
yes, ma'am. Finally, we will ask for questions, ma'am. Not till then.
Yeah,
I'm just
yes.
continuing, ma'am. Thank you, ma'am. So
Okay.
if you say like uh, what can be computed, what can be uncomputed, that itself is a major process. For example, imagine there are a lot of brain computing happening. Okay, a lot of people are working on brain computing, computational, what you can say, neurology, all that. But how a brain works can't never be completely simulated. they can work, they can simulate it to certain times, maybe 10 percentage, 20%. That's all. They are not doing more than that. It's going to be very hard for us to simulate that. But when quantum computing comes, there is a possibility you can understand the whole working of the brain. What happens when somebody sees something, how their attitude changes, how their mood is being influenced by means of brain. Okay, so everything can be simulated. So that's the best thing about quantum computing. So it's going to help us to do unsolved problems. So certain algorithms I have taken from internet. You can see, as a PG student or a faculty who are beginning their career, you can easily implement this kind of algorithms. Okay, there are a lot of quantum computing based algorithms that are available. So I have listed some. You can see I have written some algorithm. Okay, so you can see any of the algorithm, if you take for quantum computing, you can see it is based on number theory. So what do you mean by number theory? That's the basic of any of the cryptography or fundamentals of that. Okay, so this quantum algorithm is something very useful. So if you really feel like working on that, you can go for each of the small factors that are available in our algorithm. For example, if you take Fourier transform, it is basic of many of the algorithms that are available in basic computing. So how to do Fourier transform in a quantum computing can itself give a different algorithm. Okay, got it. So if you take discrete algorithms and factoring, how it is done in a quantum computing way. See, there is a paper that has been published long back in 1994. Imagine. Okay, got it. So you can just check it. Algorithms for quantum computing. How discrete logarithms and factoring is being used. You can just search it, and they have given an algorithm for database search, and how this algorithm can be used for database, and the algorithm is called as Grover algorithm. Got it? So theoretically it has zero failure rate. Imagine theoretically, but if it has been implemented, the search will be such an accurate. So imagine we have 1 lakh shelves, drawers or something at one place, and somebody like you have placed a mobile in one of the shelf of 1 lakh drawers, and you have forgot in which you have kept. Okay, so if you want to take the mobile out, what will happen? You have to open the at least half of the 1 lakh draw, and then only you can find out. The worst case is getting the mobile phone at the last 1 lakh drawer open. The best case is when you open the first drawer, you are getting your mobile. The medium cases like when you are open 50%. Okay, so but still we have a lot of cases here. But when there is no possibility that the phone will be not searched, but if it is inside one of the draw, it will be searched. But what about the computational time? What about the time for searching? That's very, very important. So only when quantum computing comes, it's going to completely change the scenario, and the search will be very faster. Okay, so and there will be new way of search. The classical computing has certain way of search, so the complexity can be identified as certain numbers only. But when you are using quantum computing, it's going to completely change the way it is being searched. So and it's going to lead to a lot of things. Okay, so if you want to do this kind of programming, there are a lot of algorithms which I have listed here. You can start doing using it, and you can do it. Okay, so you can see how algorithm of quantum is being used, like and experimental implementation of this has been done. So there are a lot of papers that are available. I have already shared this PPT with the coordinator also. So when you get time, you can just go through it, and you can go again deep searching these keywords that are available. Okay, so as I already said, why we go for quantum computing, especially in the combination of HPC, we are going to get exponential information storage. The amount of storage that is going to come up is going to be huge. Now also the amount of data we are generating this month is more than the total amount of data that has been generated for last so many years. Because every second the amount of data generated by the individual is more. It's becoming more and more almost multiple countries are converted into data storage places. Okay, so when quantum storage comes, the amount of space we need to store even more amount of data will be becoming less. Imagine we came out with something called MP3 format. What do you mean by MP3 format? It is an audio file format with one 500 MB or some amount of data CD. We can store up to 300 to 400 songs. But imagine MP3 format. It was in a different formats, audio video interface format. So we can store only in a CD or in a 500 MB devices, 4 to 5 uh, like audio or video files. But now it has developed. Now MP3 has also been overtaken, and we have even a different kind of flash storage which can be used in a multiple purpose thing. Okay, so information is encoded through entanglement. So we will be getting if you go to Google and type what are the unsolved classical computing problem, you will get, and all this can be slowly solved by quantum computing. So it's going to revolutionize cryptography, as I already told. Many of the cryptographic algorithms will be gone once quantum computer take its position. So it means we will be getting more better algorithms. It's not something to be scared of. We'll be getting much more better algorithms. So new algorithms for quantum cryptography, quantum networking will be got, and it brings entanglement, exponential power, everything into this. Okay, got it. So this is the promises that has been made, and whenever we are doing measurement, it will be very accurate. As I already told, like in sensors, we are doing accurate kind of thing, and the main drawbacks of the quantum computing, as I said, is uh, the discoherence and noises, and there are also other what you can say other kind of disturbance that are there, especially in terms of quantum error correction techniques. So if you take what are the error corrections we have here, in normal traditional thing, yeah, we have certain error corrections available. But this is going to be a new challenge, because whenever a new technology is going to be developed, first they will be concentrating only on the pros of the technology, not on the cons. So once for example, you take artificial intelligence, it was developing like anything. Multiple AI has come, and people are focusing on implementing it. Everything they can get, the AI has got into everything. Take agriculture, AI is there. Take industry, AI is there. Take VLSI, they are there. Take science, they are there. Take biology, zoology, if they are there. Imagine they are in medicine, even they are in everything. The artificial intelligence has not only swallowed the computer science department, or it has got into all other departments. Take mechanical, civil, chemical, everywhere VA is taken over. So similarly, when this quantum has to be taken over, it has to get rid of this kind of error correction techniques. Otherwise, it is going to be a problem, because the quantified noise what we get from quantum is because of the intermediate state of matter, which is there. Okay, so because we are dealing with electrons and all that, so how you can see that normal with not with normal eye, we have certain microscope to see that, and it also finds out the movements of electrons and in a or atomic level things, protons, and how it moves accordingly only we can be able to do certain things. Okay, got it. So, these are certain reports that has come in the popular press that about quantum computing. Just you can just go through it. So the infinite amount of speed we have got it, all that stuff. Like we have bit bytes. We have qubits, q gates, and q circuits. I'll just go through it very fast because I don't want to bore you. Like similarly, like we have a lot of quantum algorithms that has already been developed. So if you can just come out with your own theoretical quantum algorithm for factoring, you can come out with own theoretical algorithm for finding out the super polynomial of any number. So these are the basic mathematical foundation of computer science, and this comes as part of discrete computer mathematics, which is can be told as the fundamentals of computer science. Okay, got it. So all the problems in computer science can be divided into easily classifiable, and or that can be easily done with classical computing, or certain problems are easily quantifiable. Okay, got it. So imagine you want to find out uh, the energy or chlorophyll level in each of the leaves in a tree. Just imagine I'm taking a photo of one tree, and I want to identify based upon the color or any other attributes what is health of each and every leaf. Classical computer take time is go the time taken by classical computer is going to be very much for it, and the cost we are going to get infer about it will not let us to do that kind of research, because it's going to take a lot of speeding power and all that. Okay, so but once quantum computer comes, we can even find to the root level which root is good, which root is not good, like that. So that kind of thing is there. Here I have just shown how we are going to deal with. So efficiently solved quantum computers are between the problem that are solved by normal computer and between quantum computer. Okay, so it has placed in a very, it is very rightly positioned. Okay, got it. So why we need to go for quantum algorithms? Okay, so because as I already told it, it gives us exponential speed up, and all the things that we are using like classification, clustering, like association, all that comes under something called pattern recognition. What do you mean by pattern recognition? Anything you use morning, you go to your university or IT industry and just show your face. What it does, it takes certain attributes from your face, quantify it, makes it into a number, and search for another number that is equivalent to it. It does mean like it has already got a training database which has different images of you, or different thumbprint of you, or different palm print of you, and it has turned it into a number and it has kept. So this too is what happening. So all the pattern recognition by happens by means of Fourier analysis or any transformation, Fourier transformation. Okay, it transforms what from image to a number, and it can transform your eyes to a number. It can transform any of the like fingerprint into number. So that's what is happening. So once this quantum comes, it will be very much speeding up. And as I already told, the search is something that has been lagging. Though we have as good searches, Google searches, still it can be optimized. It can give us a very good feedback. Okay, and maximum minimum finding, and whatever it has been done by machine learning, simple machine learning to like in-depth deep learning can also be quantified by quantum computer. Okay, got it. So again, I have written a little bit about the different error correction input output challenges, but it's okay. Okay, so this is a typical quantum Fourier transform. Okay, so like don't try to understand this right now. It's going to be very hard, but I have taken it so that you will be understanding what is the purpose of doing Fourier transform. Quantum Fourier transform is something that can be done, and it is all theoretical. You need not to buy $1 billion quantum computing do it. So you can sit not many of us, especially people who are working in AAML, does theoretical computer science, but theoretical computer science is something that everybody can do just by reading certain things and coming out with some ideas. So in quantum computing, theoretical outcomes can be easily given. So like here are certain circuits that are drawn. As I told, we have something called QKit, like QuizKit. It is part of IBM, like that. Google, everybody has their own tool. But the good thing is QuizKit is like it can use normal simple programming language like Python to do any kind of writing in quantum computing. So you can see like all the quantum computing has been depicted by means of what you can say, like a circuit. So all the circuits can be used and reused. Okay, like I have given here something called SOAR algorithm, which is also like a quantum algorithm. So like it also takes into account, and it can be like used for defining new cryptographic algorithm. So imagine if you are defining your own good cryptography that is based upon quantum technology, and it works very well. Even in simulation, you can even complete a PhD out of it. That much of contribution is it. So if you are really want to work on quantum computing, rather being distracted, you can start doing your own cryptographic quantum based algorithm. This is an implementation of SOAR algorithm I have just given. So this is again a grover search, like how the search works. Okay, got it. So like for what kind of problems it can be used, for what kind of problems it can't be used, I have given example of. Okay, like the many searches are there, but this is a certain grover search is something that can be called as I can easily call as quantum search algorithm, because it can go for unstructured search and with a high profitability. So that's the main thing. Somebody is asking, you should say unstructured search with high probability. Okay, so and even it can take into account in a black box, if even like if you're not clear, then still it works. Oh god, so it again has a lot of applications like cryptography, all that. Okay, got it. So like it also helps in optimizing certain things. So these are certain, as I told you, I have given about the applications of this algorithm. Like you can see, like improved connectivity. You can use in sorting. You can finding out the length of the test, pattern matching, especially all that. Okay, so these are certain quantum inspired classical algorithm. Okay, so you saw classical algorithm, which I didn't put it here because and we saw about quantum algorithms, and now this quantum inspired classical. So it means like already you have classical algorithm. What if I give the flavor of quantum inside it? Okay, so like so this can be used for recommendation process. It's just a 15 years old purpose. Imagine they were starting to use quantum recommendation system for understanding which one is best. It can be for feedback or anything. So imagine if you are coming out with your own quantum algorithm, this will be easy. Okay, so these are certain kind of programming language that is used. You can take photo of this slide. Okay, got it. You have QuizKit from IBM, which you can use, and it's something very good to be explored. And most of this SDKs are using a larger programming language that has been used by common person, like Python and other C++ like that only. And even Google, D-Wave and Rigetti and other companies are also have their own software. So that's going to work out. Got it. So these are simple example I just told, like in order to make sure like you are okay with understanding this. Okay, so like basically these examples of are given by how we can just fix like find out a circuit. So what kind of circuit you can build by means of quantum, and how you will be measuring the circuit, and how you will be simulating all this. Okay, so similarly that's how like, so you can understand like and you can see the output of the algorithm in the second part of the slide. So like you can see the total count, how it has been. So we'll be getting the circuit also. Okay, so anybody who wants to work on any projects, so you can work on quantum error correction also, because that is some area that has been unexplored. Not many people are working on quantum error correction. So once you start working on it, you will become little popular, and your publication can also come. Okay, so like this is Shore algorithms error correcting code, other methods for error correction. So quantum simulation. So if you see like many of the simulation, as I told, like can't be simulated. Imagine you want to simulate the whole tree. You can't say a simple tree. Tree has itself its own ecosystem. It has life. It has a flow of oxygen. It has flow of water. It has flow of minerals. Many things. Can you simulate it? It's going to be very hard. But nature, the quantum, the way of simulation is based upon the nature in which the item or attribute or entity is built. So quantum way is the one that plant is built, so we can use it and get it done. So like these are certain examples of quantum simulations. Like for example, they have taken beryllium hydroxide molecule and the movement of it. So they kept it in certain treatment, and how it moves they have completely understood. And they are doing it for a water molecule on a trapped on quantum computing. So okay, so like if they take water, they're finding out what are the molecules, how it moves, and simulating that in order to find out certain solution. Okay, so you can see the difference between both of the algorithm. And the quantum advantage, as I already told, like once we get a programmable quantum computing, it is going to take some years, but it's not that it's going to stop. Like people are already working on it, and I'm very sure it's going to come up. And it's better for us to learn and understand, at least like embrace like quantum computing, so it will be easy for us. So here the number of amount of samples they are taking is in millions, so it's very hard for a classical computer to understand or to simulate this. So the quantum technologies, like we know, like we are going to derive it from engineering, like and like what are the applications? Like a lot of applications of physics. So whatever lasers, whatever imaging, MR images, CT images, whatever you are scanning, all that right from X-ray you are using is being done by physics. So quantum physics is also playing a major role, and when it becomes part of this kind of analysis or understanding, then it's going to play a very vital role. Okay, got it. So like that. Okay, so as I already told, these are the types. Okay, so this is a very important slide. As I told, like digital twin is something that we can use in quantum computing. Got it? So like if you take 85 to 2002, digital twin was just a concept. Okay, so like it's focused on R&D, like so it's the same to same, like whatever we have, we had the same thing only. Okay, so like coming out with graphs, coming out with model, coming out little bit of remote programming and all that stuff. On the other hand, if you take after 12 years from 2003 to 2024, we have got into a lot of new way of building it. So we came out with 3D printing, and it has gone. 3D printing was invented long back, but because of patent certain policies, like it was put to public after so many years, and people started using somewhere around 2003, like that. Okay, got it. So like virtually we were assembling cars, virtually we were assembling industry, and simulation has been done. Oh god, so like then after that you can see like for 14 to 16 you got a huge breakthrough in simulation, because whatever you want to do you can simulate by means of IoT connected devices, and data unification between the physical and virtual world has been done. Okay, so there has been rapid feedback across design, manufacturing, operations, and all that. So now you can see like afterwards now we have got heavy amount of simulation that are available. Like it's part of mixed reality, cognitive, and AI. So we have holographics, we have AR, VR, which performs optimal simulation. So once with AR, VR, you can do any kind of simulation that we want to do in real world. So then it also has cognitive service, AI, all that. So anybody who wants to do research in digital twin, I am very sure it will be very useful. And when you're using digital twin and quantum, it's going to really help. And these are certain topics that not many people are working. Not many people know also. So once you take this, it's going to really work. And there are companies which are putting a lot of efforts. Like for example, if you take Siemens, it's a company which is into digital twin. So they do unmatched visualization. Like many of the other companies are also working on it, and it is based upon quantum networking or any of it. So you can also like work on this kind of quantum twin kind of technologies. Okay, so what you'll do in quantum twin is digital representation of an intended or actual real world physical product. Okay, so what you do in a real quantum device can be like taken, and it can be like done in a simulation. So instead of playing really with the atomic structure of any of material, you can just take yeah, programming, and you can do simulation. Even a quantum programming like that is written with Qiskit is also representate a model or simulation of real time platform. So if you are making the software work, it I'm very sure it's going to work in the real time also. Okay, what? So like now people are working on something like how they are bringing in high performance computing and quantum computing together. Okay, so like we have to be very sure. Like already we have high performance computing infrastructure. You know that like company like Qualcomm are investing so much, and initially we used to have normal processor, then became dual core, multi core, quad core, all the processor came. Now we have got from CPU to GPU, and very slowly the CPU will not exist, only GPU will take back every power of CPU, because the GPU can do any kind of operations in seconds, which can be done by CPU in minutes. Okay, so like it has come out in a very well manner. So now how to, already AI has been part of the chip industry. I already told you the way that we're designing chip, and the way the chip is being put into operation is much better. So like that. So this is an image of the quantum computer of IBM. As I told, it's very expensive. It is being like in multiple millions of dollars. Like so what it has pipes that will be able to understand the movement of any liquid or material in a certain form, and this device is being kept in a very cold, under 40 or 50 degree temperature. Okay, like that. So the scenario what we can talk about is like what are the systems and how we can create for the systems a quantum state, and then how we can do solve that by calculating the energy, and how we can make the parameters using energy, and we can keep on repeated. So there is a kind of handshaking between the classical computer and quantum computer, which is possible. And because of this, a lot of achievements can be done on all this prescribed area. If you take manufacturing, automobile construction, on energy, healthcare, transportation, medicine, retail, smart cities, and sports and athletics. All this I can give n number of applications. And if you see the trends in which all this quantum technology is being used, then you can say like quantum sensors. A lot of people are working on quantum sensors, especially 17% of the people who are working on quantum or working towards quantum sensors. And next comes novel qubits and hybrid quantum applications. A hybrid quantum application is something that we are talking, like we were talking that how to combine classical and quantum computer and get it done. Advanced materials, post quantum cryptography, quantum simulation, fault tolerance computing, cloud computing, quantum machine learning. Okay, all this stuff. Okay, so like there is a possibility we can use HPC, AI, and quantum computing, which is a very good combo. So once these three form pairs between them and work, the synergy between these three technologies is going to really make things better. Okay, got it. So like imagine a laptop computer with a single core processor and a couple of gigabytes memory can even help us to land any of the moon kind of satellite. When this kind of computing power comes, we can do anything. Like we can do anything that is not possible, because all the world runs by means of computational power. The more the power you have, the more better your operations and computing will be. So that's going to pave way. Got it? So like adding AI to HPC integration. So analyzing whether optimal computing should be HPC, QC, or neither. Like how we are going to analyze HPC should be accelerate for like what is going to help what, or how they are going to help each other. Either they are going to share computational resources, or they are going to simplify the library and framework, or they are going to integrate all these frameworks together. And what is this? This is the billion-dollar question. A lot of people are working towards it. On the other hand, they are also finding out errors in measuring and all that stuff. So I'm just showing some of the publication, not as an advertisement, but to say that this some publication that I have done before few years also. Now also we are doing a lot. Like you can see, like this we it is a small concept and a small contribution that has been done by for quantum communication. We came out with a quantum channel optimization, like how we can integrate quantum inspired machine learning with genetic adaptive strategies, and immediately it got published without much of revisions. That is the power of quantum, because each of the journal doesn't have much of quantum technology related things inside them. Okay, got it. So these are some of the books that we have done. We have I myself I have done more than 200 books. Like this, I am doing more books on quantum computing nowadays, because even the editors, publishers, they ask me, Bala, can you write books on quantum computing related? So this we come in quantum and blockchain. So because many new technologies only they want books for. Okay, so because once we get rid of the noisy environment, it's going to work. So like you can see, like I already told while beginning the lecture, like we have GPS satellites coming up, and if you take electromagnetic field sensors and all that, lot of things are happening. So the applications of quantum computing is not minimal. If you take applications of that in healthcare alone, like it's going to be like too much. For example, if you are taking any of the drug research, or if you're taking personalized medicine, or a remote healthcare or radiotherapy, all will be done by means of quantum computing only. So understanding the quantum impact in for healthcare itself is a big research, and how industry challenges in healthcare are going to be taken care itself is a bigger challenge. Okay, got it. So the applications of healthcare and biomedical are not limited. So imagine like we have a medical imaging, geological survey, and nuclear monitoring, gravitational detector, all that. It's going to really help us. So like we have already got accelerometers, gyroscope, and all that, but which is used for autonomous transportation. Now it will become even more this one. So if you take especially electrical vehicle, that too the autonomous driving vehicles. So they need precise thing. So they all the sensors also need precise, but like it has to put the brakes or it has to do any action as when a human brain driver is driving. Okay, it has to be very very careful, and it also has to drive in high speed or low speed or medium speed according to the need. So that time this quantum technologies can help them to uh, find out a better place. So that's what I wanted to say. Like, and if you say like, ma'am, how many minutes is more for me?
So it's 20 more minutes.
Okay, ma'am, perfect. Okay, got it. So, like when you are using this kind of simulators, especially quantum simulators, you can find out and you can even understand the power of quantum by adding it with HPC. Like as I already told, though we need specialized hardware, and we need specialized processing units, but still, instead of just doing waiting for this quantum to be developed, we can integrate with classical computing, and we can do all the needful things. Okay, so that's going to help us with the challenges, opportunities, and it has to give, and it will be giving a right solution. Okay, got it. So how a person has to start? So he has to start working based upon the principles of quantum mechanics, which is already available, and quantum computers perform certain thing, especially if you take a biomedical problem. So where the complexity is high, like for example, if you take like how the molecules interact in your body, how the proton unfolding happens, or how you are going to come out for a drug discovery, everything this can also be done. So already we have in the field of genomics, like how artificial intelligence works, but quantum computing is going to help us in a very different way, like if you go for cryptography, network analysis, all that. So that's where we have to put all our effort. Got it? So the quantum computing, which is very different from what you can say like quantum mechanics, is it's a very different way of finding out what is that needed. And it's not only depend upon computing, it also include many of the thing inside it. And we were talking about examples of different kind of large scale healthcare problems that can be taken into account. And it not only that, it has it can combine everything. For example, if you take the quantum computer, how it came, like if you take if you take the processing side, already we have got a company has come out with a certain processor, Intel 1 2 3, like that. It has gone multiple process, all that, and the processing is very high. If you take database, we have brought multiple GBs of data inside a small pen drive by means of flash drive. So the database, and we have a lot of cloud environment which can help us to navigate or deploy any kind of application and scale it within seconds. If you take Amazon Web Service or Google uh, like cloud, anything, it gives scalability. All the applications, whatever applications you take, either your tech applications or your healthcare application, it's on running on cloud. Nobody owns a server nowadays. If you go to even a big facility, you can't find a server room at all, because everything has a cloud environment, and people are using the cloud environment to do that. Sorry, I think the slide got this one. Okay. Okay, like you can see, can you see my slide? Yes, okay, I think I can. Okay, got it. So whenever, for example, if you're writing a funded project on cloud computing, what is that you will write? Okay, that's very important. Especially in healthcare, we can discuss, and how we can you can write a funded project by which you can understand and analyze the building blocks of implementation of quantum healthcare service. That can also be there, and how future we can use. Okay, so if you take classical computing, where computing units, computing capacity, sustainability, how this can be used here also can be discussed. So like that, many paper has come outside. So you have to just go through it. So how you can even do a review on how come quantum computing is important to healthcare, how I can use it in terms of power efficiency, in terms of maybe processing power, or in terms of like what I can say, like multivariables, robust intelligence, or something like how adaptable it is, like that. Okay, so if you take medical image analysis, there are a lot of things. Now we are even using edge computing, fog computing, and all that. But once this medical imaging analysis come, it's going to be very easy for us to do. And drug design, you just imagine you have you have tablet like paracetamol, which and all will take at least 15 to 20 years for like building it, because they have to do a lot of analysis before coming out with that kind of like drug design. So but we can, this quantum computing will add a catalyst and do the things faster, maybe in 1 or 2. Imagine during COVID period, the people came out with vaccines, a lot of companies came out with vaccines within a year, so which is a miracle. Like they would have used a lot of computing power and many manpower and all that stuff, with the help of multiple private and government organizations, then only they would have got. Otherwise it's not very easy, like to get a vaccine and all that stuff. Okay, got it. It's similar to that. So like whenever you are using you want to do something, you just go to a research lab called Oak Ridge Leadership Computing Facility. You can go to the web page, and they have done a lot of research. Okay, got it. So they have come out with GPU accelerators. They name it as Titan, Summit, and Frontier. Okay, so like they have used this for doing a lot of operations. So like the steps what they have done is like what kind of mission can be done by means of this facility, what are the alternate that are available, what are the benchmarks, all that stuff. So you can also get into that, like what you can say, OLCF or Oak Ridge Leadership Computing Facility, and you can see that. So we does also need a quantum hardware, which is not very easy. It's a very novel hardware which we have to use. Okay, so a lot of researchers are going on this quantum hardware, so you can also be part of the research. So you can find out what kind of hardware is needed, and how we can get like the supercomputing or superconducting quantum materials. Okay, got it. So like how the circuits can be designed so that it can be part of CPU, GPU, and QPU. Okay, quantum powering unit. So how we call a CPU computing powering unit and GPU graphical power unit. We are going to get GPU quantum power unit. Okay, like that. So how we measure how many qubits can be used, how it can be accelerated. That's how we use. Got it. So like uh, this can be done by means of quantum circuits that are there. So like okay, so this I have just given a picture taken from a journal to understand how resource management or allocation is done in quantum computing. So you can just see to that. So we have other programs that are part of this. If you want to access this, you can do it. Where people say like I can't do projects, I can't write fundable. No, we can do. There are a lot of projects that are going on lively, and you can also do certain projects through this, and you can part of the team, and you will also be part of the newsletter that comes, which gives us like entirely different way like how quantum computers being used. So these are certain quantum level that are there. So you can see what countries are working on what. Each of the country has their own research lab. You can even go to the Indian quantum computing movement. This new devices are being done. Okay, so especially this Oak Ridge National Laboratory, you will be able to connect and get the quantum time for if you have really good research problem for them. So these are now people are working on benchmarking the quantum system, and they are coming out fully functional facility environment for quantum. So these are certain um, computational thing that are available in quantum computer, which is available ORNL, which these are certain datas I have put. So I have talked about quantum hardware. So as I told, like we are dealing with trapped ions, we will they are taking into account whether how it is possible to for a diamond to be taken into account as a device of quantum computing, like how we have silicon for classical computing. Like they are also like working on different hardware equipments. So like you can see how HPC and QC can be integrated, all this stuff. So if you want to be part of this uh, quantum computing interface, you'll be able to do this. Like you can get into this QCUB project, which will be giving you new avenue to explore new computational research, and you can be part of the research. And they have given a lot of applications for it. So there is also in already available software ecosystems that are available, simulators available, and if you start with, you can use Qiskit for using that. And I have also given in the last day how to install Qiskit. That will be easier, and I also given further reading what is it. Thank you for the time. If you have any question, let me know. I'll be able to answer.
So, participants, if any questions, you can type in the chat box. So there's one question regarding the proposal, like if they want to write a proposal in quantum computing, what may be the claim for hardware and software requirements?
It is very hard to define the hardware needed because it will be in multiple crores and they will not be able to fund it. But software there are there. A lot of proprietary softwares are there. I have listed in the name of the software in my PPT, so you'll be able to get it. Some of the softwares are free for certain particular use, but when you want to develop it, it's a proprietary. You can ask for that, and it comes per hours usage. And in case if you want to solve certain critical problem, certain companies are giving their quantum computing time for free. How we get Amazon Web Service cloud timing for certain time they have given. You can just understand it and you will be able to use it.
Thank you so much for your time, sir.
Thank you. Thank you, ma'am. Have a nice day, nice organization. Please continue with your validation. Thank you. Thank you,
Yeah,
Shiva.
thank you, sir. Thank you so much for your time.
Thank you.
Participants will be starting the validatory in 3 to 5 minutes. I will be sharing the feedback link for this session. Please fill the feedback link.